Welcome. In this session, we build a brand perceptual map using text data, specifically customer reviews. The main idea is simple. Customers already describe brands in their own words. We will treat those words as evidence about brand associations, and then quantify how positively or negatively each association is evaluated. As we go, keep one promise in mind. We are not trying to produce an abstract two-dimensional map with mysterious axes. We are building outputs that managers can read immediately: a heat map, a two-association map with named axes, and a dashboard that separates salience from favorability. Here are the outcomes to keep in view. By the end, you should be able to take a review dataset, discover association candidates with topic modeling, attach an evaluation signal like rating-based favorability, label associations so they are business-friendly, and then produce 3 interpretable outputs. We will also add one optional layer at the end, an embedding-based deep dive for a single association to explain what people praise versus what they criticize. That embedding step is intentionally scoped so it supports interpretation instead of replacing it. In this setup cell, we install and import the tools we need: basic data science libraries, scikit-learn for topic modeling, and sentence transformers for the optional embedding deep dive later. We also set a random seed once so results are repeatable across runs. Finally, we check whether a GPU is available. A GPU can speed up embeddings, but the core of this notebook, including topic modeling and the perceptual map outputs, runs fine on CPU. Let's ground the motivation. Classic perceptual maps often come from surveys. That works, but it can be expensive and slow to refresh. Text data gives us a scalable alternative. Reviews already contain the language of associations: durable, easy to use, cute design, poor quality. Our job is to convert that language into structured, interpretable signals. We will use a simple evaluation signal: rating-centered favorability, defined as rating -3. So 5 stars contributes +2, 3 stars contributes 0, and 1 star contributes 2. This pipeline stays interpretable end to end. We fit a topic model so topics become association candidates. Then we compute, for each brand and topic, salience, favorability, and favdim. Next, we label topics into business-friendly association names. Then we produce 3 main outputs: a favorability heat map, a two-association map with named axes, and a salience versus favorability dashboard. Finally, we use embeddings only inside one selected association to explain what is praised versus criticized. Part 1 is about getting the data into a standard format. Throughout the notebook, we assume 3 columns: brand, text, and rating. If you already have a clean dataset with a brand column, the local CSV option is the best choice. If not, we use a public Amazon reviews dataset from the Snap repository as a realistic fallback. Either way, the goal is the same: produce a working data frame called DFUs that we can reuse for every step that follows. In this code cell, we implement 2 loading paths. First is the local CSV hook. If you set local CSV path, we infer brand, text, and rating columns and standardize them. Second is a public fallback from the Snap Amazon Reviews repository. We stream compressed files, map products to brands, and collect review text. Notice the balanced sampling logic. We cap the number of reviews per brand so later comparisons are not dominated by one brand. Now we clean types, filter low-quality rows, and compute favorability. First, we ensure brand is a string, text is non-empty, and rating is numeric. Then we filter out very short reviews and missing ratings. Next, we keep brands with enough reviews and then select the top brands. In the demo run shown in the notebook outputs, we end up with 8 brands and a balanced dataset with the same number of reviews per brand. That balance is useful because it makes heat maps and maps easier to interpret. Finally, we compute favorability as rating -3. That means A 5-star review becomes +2, a 3-star review becomes 0, and a 1-star review becomes 2. This favorability signal is intentionally simple. Later, you could swap in sentiment model outputs, but the workflow stays exactly the same. In part 2, we build text clean, the text we will feed into topic modeling. The philosophy is, keep it simple, do not overclean and preserve meaning. Overly aggressive preprocessing like heavy stemming can make topics harder to interpret because it removes the natural words that we want to use as labels. So we do just enough cleaning to remove obvious noise while keeping the language of the customer intact. This cell defines a minimal cleaning function. We lowercase the text, remove URLs and HTML line breaks, and remove most punctuation while keeping apostrophes. Then we normalize whitespace. The output is a new column, text, clean, created with a progress bar so you can see the transformation run across all reviews. A good rule of thumb is, after cleaning, you should still be able to read a review and recognize it as natural language, not as a bag of fragments. Before moving on, we do a few quick checks. We check the empty rate to make sure our cleaning did not wipe out content. We look at length statistics so we understand how long reviews typically are, and we sample a few before and after examples to visually confirm that meaning was preserved. Here we compute 3 diagnostics. First, the empty text clean rate. Ideally, it should be near 0. Second, descriptive statistics on cleaned length. Third, a small random sample showing the original text and the cleaned text side by side. In the demo run, the empty rate is 0 and the median length is a few hundred characters, which is typical for product reviews. That tells us we have enough content for topic modeling without heavy pre-processing. Great, we now have the cleaned text needed for modeling. Part 3 is where we turn raw text into association candidates. We will use LDA, latent Dirichlet allocation, as a simple and widely used topic model. LDA assumes each review is a mixture of topics, and each topic is a distribution over words. The key output is the matrix theta, written as theta ik. This is the probability that review I belongs to topic K. So for any given review, topic probabilities sum to 1. A high theta ik means that review is strongly about topic K. Why does this matter? Because T lets us do soft assignment later. Instead of forcing each review into one bucket, we can weight its contribution to multiple associations based on how strongly it expresses them. This cell does 2 things. First, we convert the cleaned text into a bag of words matrix using count vectorizer. We keep common settings like English stop words and minimum document frequency, so rare tokens do not dominate. Second, we fit an LDA model with K topics. Here K is set to 10, meaning we are discovering 10 association candidates. After fitting, we display a top words table. For each topic, we list the most probable words. This table is the first hint about what each association might represent. For example, in a baby product dataset, you might see a topic dominated by words like crib, sheet, soft, suggesting a bedding association. Now we compute doc topic, the theta matrix. We then summarize prevalence in 2 complementary ways. First, average theta across all reviews tells us which topics are most common overall. Second, an argmax assignment count gives a beginner-friendly approximation. For each review, which topic is the largest and how many reviews are assigned to each topic. In the demo output, a couple of topics have noticeably higher prevalence than others. That is common. Some associations are simply discussed more often in the category. This information is useful later when we decide which associations deserve the most managerial attention. Top words are helpful, but they can be ambiguous. Words like great or use appear in many contexts. So we add a second form of evidence, representative reviews. For each topic, we will show a handful of reviews with the highest theta for that topic. Those are the reviews that are most purely about the association, and they are the best material for labeling topics into business-friendly names. This cell prints representative reviews by topic. For each topic, we show top words and a few reviews, with the highest theta for that topic, along with rating and favorability. Skim, do not read everything. The goal is to confirm what the topic actually means so you can label it responsibly. Here we add two convenience columns to DFUs. Top topic ID is the topic with the highest probability for the review. Top topic prob is the value of that maximum theta. We avoid adding every theta column to keep the data frame clean, but these lightweight columns are useful for quick slices or sanity checks, especially when you want to browse examples of reviews dominated by a particular topic. Part 4 converts topics into interpretable brand by association metrics. For each brand B and association K, we compute. Salience represents how much customers talk about this association for the brand. Favorability menas, whether the association is praised or criticized, computed as a theta weighted average of review favorability. FAVDIM, a combined positioning score, roughly presence times evaluation. The unit we interpret is the association itself, not abstract DIM1 and DIM2 axes. This cell creates the core tables, DFSAL, DFFAV, and DFDIM. We loop over brands, take the subset of reviews for each brand, and aggregate using the topic probabilities. Salience is the mean theta by brand. Favorability is the weighted average of favorability by topic using theta as weights. FAVDIM is the mean of theta times favorability. After this cell runs, we have a complete brand by topic representation. Think of each row as a brand and each column as an association candidate. Everything from here on is about making those columns interpretable and actionable. Before labeling, it helps to peek at the structure. This helper section shows which topics are most salient overall, and for each brand, which topics are most salient. It also provides a quick example for one brand showing the best and worst topics by favorability. Even though the columns are still topic IDs, you can already see patterns. For example, one brand may be heavily discussed in a crib sheets topic and evaluated very positively there, while another brand may be discussed in a gate or safety topic with mixed evaluations. This is a preview of the competitive structure we will reveal more cleanly after labeling. Labeling is the interpretability gateway. A topic model gives us statistical clusters of words, but managers need association names. So we translate topic IDs into short, consistent noun phrase labels like quality and durability or ease of use. We will use a practical workflow. Auto-labeling provides a quick suggestion to reduce workload. Manual labeling is the final decision because you are accountable for what the label claims. The evidence you should rely on is always the same. Top words plus representative reviews with the highest theta for that topic. This cell prints a labeling worksheet. For each topic, it shows top words and a few representative reviews with the highest theta. Use those examples to choose a short noun phrase label that you could defend to a manager. If two topics truly reflect the same association, you can label them the same and merge later, or refine labels to separate sub-themes. Either choice is acceptable if the text evidence supports it. Next, we generate auto-label suggestions. Auto-labeling here is not a large language model. It is a simple keyword matching rule that looks at the topic's top words. The goal is speed, not truth. If the auto-label makes sense, it saves you time. If it looks wrong or too generic, you override it using the worksheet evidence. This cell defines a small dictionary of label categories and keywords. For each topic, we take the top words, count how many keywords match each label category, and choose the label with the highest hit count. We also keep a match score so you can see how strong the evidence is. Two common issues appear immediately. First, some topics get other needs manual label because no keywords match. Second, multiple topics may receive the same label like ease of use, installation. That can happen because the auto dictionary is coarse. This is exactly why auto labeling is only a starting point. The worksheet plus your judgment is what produces clean, interpretable association names. Now we finalize labels. The notebook is designed so you can edit a simple list called association names, where association names is the final label for topic K. When you label, follow 3 guidelines. Use short noun phrases. Keep granularity consistent across topics. Avoid duplicates when possible unless you intentionally plan to merge duplicates. If you do see duplicates, do not panic. Duplicates can either mean the model split one association into subtopics or that your label categories are too broad. In the next steps, we show how to handle duplicates safely. This cell is the final labeling checkpoint. It supports a practical fallback order. If you already created association names, it uses them. If not, it can load labels from the auto-labeling table. And if neither exists, it falls back to a readable label built from the top 5 words, like T2, sheet, soft, crib, mattress, fit. That ensures the notebook remains runnable even before you finish manual labeling. Then it runs 2 quality checks. It flags placeholders like needs manual label, and it flags duplicate labels so you can decide whether to refine or later merge. This cell produces a final label map table, topic or ID to association name. That table is a key deliverable because it documents your labeling decisions. Now we apply the labels. We replace topic column names with association names in DF-PO-SAL, DF-PO-SAF-AV, and DF-PO-DIM, producing DF-PO-SAL-DUCE labeled, DF-PO-FAV-DUCE labeled, and DF-PO-DIM labeled. We also freeze plotting orders. Associations are ordered primarily by average salience across brands, so the most discussed associations appear first. Brands are ordered by review counts, so more stable estimates appear at the top. If your labels include duplicates, you may temporarily see repeated columns at this stage. That is okay. A robust merge step is applied before the 2 association map to keep the plots interpretable. Great. At this point, we have labeled interpretable tables. From here on, every plot and dashboard can be read in association language, not in topic IDs. Next, we step back and reframe what an association means in this lecture and how to interpret the 3 signals we have built. Now we change the way we read results. We are not trying to prove that brands are different. That is trivial. We want to explain how brands differ, association by association, and whether those associations are praised or criticized. So the interpretation unit is an association, meaning a topic with a business-friendly name. From here, we will follow an interpretation first order. First, the heat map shows the full landscape. Second, the 2 association map gives a named 2-dimensional positioning view. Third, the dashboard separates salience from favorability for one association. Finally, embeddings help explain why, but only within one selected association. This is the core method. For each brand and association, we read 3 signals. Salience answers, do people talk about this association for this brand? Favorability answers, when they talk about it, is the evaluation positive or negative? FAVDIM combines the 2, so it can be used as a positioning score in a 2-axis map. A simple mental model is salience is volume, favorability is valence, and FAVDIM is volume times valence. For example, if quality and durability is highly salient and highly positive for brand A, that is a core strength. If it is highly salient but negative for brand B, that is an urgent pain point. If it is low salience but very positive, it is a hidden strength that might be undercommunicated. This cell generates 2 quick interpretation tables. First is an association summary across brands, average salience, and the variability of favorability or FAVDIM. High variability means the association separates brands. Second is a brand quick readout. For each brand, the most salient associations, the most praised, and the most criticized. Use this as a short verbal preview before you show the heat map. Now the embedding idea carefully scoped. A common mistake is to compute one embedding per brand using all reviews, then map brands by embedding similarity. That mostly measures overall semantic similarity and often produces plots that are hard to interpret. Instead, we use embeddings only inside one selected association, after we already know the association's salience and favorability patterns. Within that association, embeddings help answer a very concrete question. what is praised and what is criticized. We will build positive meaning and negative meaning within the selected association and then show representative review snippets that best match each meaning. This makes embeddings interpretable because the explanation is grounded in actual text evidence. We will use two ways to connect reviews to an association. Soft weighting uses data as weights for every review. This is best for the main tables and plots because it is stable and uses all data. Hard filtering selects reviews that strongly belong to the association, meaning theta IK is above a threshold. This is best for the embedding deep dive because the meaning is cleaner and the example snippets are easier to interpret. If hard filtering yields too few reviews, we relax the threshold. This gives us a practical, teaching-friendly workflow, stable main outputs, interpretable deep dive explanations. This cell produces two outputs. First, a comparison table that explicitly states where we use soft weighting and where we use hard filtering. Second, a threshold preview. For each topic, it counts how many reviews have theta above 0.6, 0.5, and 0.4. This is a simple way to anticipate which associations will have enough high-purity reviews for an embedding deep dive. When you teach this, you can emphasize that model-based tools are not magic. You always check whether the data supports the analysis you want to run. Now we produce the first main output, the brand by association favorability heat map. This answers a direct managerial question. For each association, which brands are praised and which are criticized? When you read the heat map, look for two patterns. Column patterns show associations that separate brands. Row patterns show where a particular brand's strengths and weaknesses live across associations. This cell plots the heat map. We order associations by average salience, so the most discussed associations appear first. We optionally order brands by review counts for stability. Interpretation is straightforward. Brighter values mean more positive association level evaluation, and darker values mean more negative evaluation. When you see a strong contrast within a column, that association is a competitive battleground. When you see a strong contrast within a row, that brand has clear strengths and weaknesses that can be translated into positioning and action. A key teaching moment here is that we are reading named associations, not abstract dimensions. The map is already interpretable before we create any 2D plot. Here is the key constraint for the 2D map. We do not use abstract dimensions like dim1 and dim2. Instead, we pick two associations and use them directly as the axis. We will position brands using favdim on each axis. Favdim is useful because it reflects both salience and favorability. So this 2D map answers, if we focus on these two associations, how do brands position relative to each other? Think of it as a scenario-based perceptual map. We choose the scenario by choosing the two associations. This cell chooses the axis in a practical way. The default rule is pick associations with the largest variance in favdim across brands, because those are the associations that separate brands most strongly. At the same time, this cell handles a common labeling issue: duplicate association names. If duplicates exist, it merges duplicate columns by summing them, which restores a single column per association. That keeps all later plots interpretable. In the demo output, the top axis candidates include quality and durability and ease of use installation. That makes intuitive sense. Those are often high-impact associations in product categories, and they vary across brands. Now we draw the two association map. Each point is a brand. Moving right means stronger positioning on the X association. Moving up means stronger positioning on the Y association. Because the axes are named, you can immediately tell stories like strong on quality but weak on ease of use, and identify close competitors as brands that sit near each other on both axes. A simple way to teach the map is with quadrants. Top right means strong on both associations. Top left means strong on the Y association but weaker on the X. Bottom right is the reverse. Bottom left means weaker on both relative to the peer set. You can also read gaps. If there is an empty region in the top right that suggests a positioning opportunity, an association combination that no brand currently owns. Finally, remind students that this is not the only map. If you pick different associations, you get a different strategic view. That is a feature, not a bug. TF-IDF is useful, but it mixes two things, salience and favorability. So part 9 separates them. For one selected association, we plot x-axis as salience, meaning how much customers talk about it, and y-axis as favorability, meaning praised versus criticized. This is often the most actionable view for managers. High salience and negative favorability is a clear pain point. High salience and positive favorability is a strength worth defending. Low salience and positive favorability can be a hidden strength, and low salience and negative favorability is typically lower priority. Here we choose which association to analyze in the dashboard. The notebook prints the most salient associations overall, and by default it reuses one of the 2D map axes for continuity. You can override this manually if you want to discuss a specific association that is strategically important. This choice is a good moment to emphasize managerial judgment. The model can suggest candidates, but the analyst chooses the association that matches the business question. This cell plots the dashboard scatter. The x-axis is salience and the y-axis is favorability. We add reference lines, median salience, and zero favorability. Top right is a visible strength. Bottom right is a high salience pain point. When narrating, pick 2 or 3 brands and explain their quadrant in plain language. This cell turns the dashboard into a simple table. For each brand, it assigns a quadrant label such as high salience, positive, meaning a strength. High salience, negative, meaning a pain point. Low salience, positive, meaning a hidden strength. Low salience, negative, meaning low priority or niche. This is a great teaching device because it shows how analytics outputs become managerial categories. You can also use it as a bridge into action planning, what to protect, what to fix, and what to monitor. This part is intentionally narrow. We do not build a new perceptual map with embeddings. We use embeddings as an explanation layer inside one association. The goal is to summarize meaning in a beginner-friendly way. Positive meaning is what customers praise within this association. Negative meaning is what customers criticize within this association. The high-level steps are: select the association, select reviews that are strongly about it, compute embeddings, build brand-level positive and negative meaning vectors, and then show representative snippets that are closest to those vectors. The reason this works is that we end with text evidence, not just vectors. That makes interpretation concrete. First, we map the selected association name back to a topic ID. If multiple topics share the same association label, the notebook warns you and picks the first match. This can happen when auto-labeling is coarse or when the topic model splits one association into subtopics. For teaching, you can point out that this is a labeling design choice. If you want a cleaner deep dive, you can either refine labels to make them unique, or you can merge the underlying topics before this step. The cell also shows the top words for the chosen topic as a quick reminder of what the association represents. Next, we choose which reviews to include for the deep dive. We start with the hard filter. Keep reviews with theta IK above a threshold tau. This keeps the meaning clean because every selected review is strongly about the association. We try a few thresholds from strict to lenient. If we still have too few reviews, we can fall back to a softer approach, but hard filtering is the best default for teaching and interpretation. This cell implements the selection logic for the deep dive. We choose a theta threshold that yields enough reviews, then add theta to the selected rows for transparency. Next, we cap reviews per brand to control runtime. Pay attention to the brand counts. If one brand dominates the topic pure reviews, the deep dive will mostly reflect that brand's language. If that is a problem, relax the threshold, change the association, or use a softer weighting approach for the deep dive. Now we compute sentence embeddings for the selected reviews. We use a compact pre-trained model from sentence transformers. The cell shows a progress bar and prints the embedding matrix shape. If you see a hugging face token warning, that is just an authentication notice. Public models still download fine. And if you are on CPU, it may take longer, but the notebook remains runnable. Remember, embeddings here are not used to create an abstract map. They are used to retrieve representative examples that explain praise and criticism within the association. This is the key interpretability step. For each brand, we split reviews into positive and negative based on favorability. Then we build two vectors, a positive meaning vector, weighted by how positive the reviews are, and a negative meaning vector, weighted by how negative the reviews are. We also require a minimum number of positive or negative reviews to create a stable vector. That means some brands might not get a negative vector if they have too few negative reviews within this association. The resulting table tells you which brands have enough evidence for a positive and/or negative meaning summary. That helps you avoid over-interpreting sparse data. Here is the interpretation rule. Positive meaning is not the same as positive sentiment in general. It is positive meaning within this association. So if the association is quality and durability, positive meaning will capture phrases like soft, fits well, or holds up after washing. Negative meaning will capture complaints like shrinks, rips, poor stitching, or breaks quickly. The point is that the embeddings give you semantic summaries that you can translate directly into product insights and marketing claims, supported by representative snippets. Now we retrieve examples. For each brand, we compute cosine similarity between review embeddings and the brand's positive or negative meaning vector. Then we take the top snippets and print them with their similarity scores, ratings, favorability, and theta. This is where embeddings become interpretable. Instead of saying the vector suggests durability, you show two real reviews that best represent praised durability and two that best represent criticized durability. When you narrate this cell, read one positive snippet and one negative snippet for one focal brand. That is enough to make the concept stick without spending too much time. Optional extension within association competitive sets. We compute nearest neighbors between brands using cosine similarity of their POS vectors and separately their NEG vectors. POS neighbors show who gets praised in similar ways within this association. NEG neighbors show who share similar complaints. Use this sparingly. It is most helpful after you have already told the core story from the heat map and dashboard. Part 11 is about translating analytics into action. A clean way to summarize the workflow is, the heat map tells you what is praised and criticized across associations. The to association map tells you where you stand on two named dimensions. The dashboard tells you whether your position is driven by salience or by evaluation. And the embedding deep dive tells you why, using concrete text evidence. Now we turn that into a short manager-ready narrative and save the artifacts you would use in slides or a report. This template is designed for speed and clarity. Sentence 1 states, positioning on the two named associations. Sentence 2 lists the most praised associations and the biggest pain points, ideally emphasizing cases where salience is high. Sentence 3 proposes action, protect a strength, fix a pain point, and identify an adjacency opportunity. If you use this consistently, your analytical outputs become repeatable managerial language, which is exactly what makes this approach useful in practice. This cell generates a one-page readout for a focal brand. It summarizes two-axis positioning, top praised and criticized associations, and high salience pain points. It also suggests a simple adjacency opportunity by looking at nearby brands in the two-axis space. The goal is a manager-ready first draft that you can refine with domain knowledge and, when available, a small piece of text evidence from the embedding snippets. Finally, we export the deliverables as CSV files. The most important outputs are the topic label map, which documents how topics became associations, brand by association salience, brand by association favorability, and brand by association favdim for positioning. These tables allow you to rebuild the heat map and maps in other tools, and they support slide building and reporting without rerunning the full notebook. Thank you for watching this lecture. See you in the next class.